we live nowadays, if you really think about it, in reality where most of the technology we use, like this one as well, is not built here. It's built abroad. And so the question that the next speaker raises is maybe it's not about who made it, but what is running on it. And his argument is that the greatest vulnerabilities lie not in the machines themselves, but in the invisible code that lies in them. So let's welcome on the stage a global leader in industrial cybersecurity and regulatory strategy. Let's welcome the President and CEO of AMPYX Cyber, Mr. Patrick Miller.
Thank you.
Welcome, Patrick.
Thank you.
And the clicker is right there.
There it is. All right.
Good luck.
Okay, very, very difficult to follow that last one. Yeah, we're talking about trusting the hardware. We'll talk about how far you can trust the hardware, but we're talking next is what's right above the hardware. Between the hardware and the operating system is where we're going to go. Basically, reasserting your own assurance here. Here's a long list of things. I've done some stuff. Regulatorily, I was one of the first architects of the NERC CIP standards in the US. This is 20 plus years ago. So I've actually written federal regulation to secure power systems across all of North America. I've worked in South America and in Europe. Our European office is in Estonia, but have a deep understanding of the industrial and OT world. So Anastasia's presentation was near to my heart. So the premise of this talk is the threat is not coming, it's already installed. This is a reality I would like everybody to come to at the end of the talk. So in this case, the context of the discussion is more about, I'm going to use power system examples, and luckily we just had a good power system talk, so hopefully this is fresh in your mind, but this can apply to any infrastructure. So with OT systems, whether it's trains on a rail, water in a pipe, electrons on a wire, boxes on a belt, it's all flow control. It's basically all the same thing. A lot of the hardware is even the same. A lot of the protocols are even the same. So this can apply across the board. And then the next thing is when I say firmware, for the technical people in the room, I actually mean all of the firmware things. So not just specifically firmware, but everything from UEFIs, bootloaders, secure boot mechanisms, option ROMs, read-only memories, these kind of things as well. So just there's a wider picture. Okay, now, why does this matter now? Why are we worrying about this at the moment? Supply chain is a strategic weapon at this point. The target here is control of the environment, but without some sort of detection mechanism. The sophisticated actors today, the threat actors that we're looking at that want to get into really important things like critical infrastructure, they're targeting things below the human, below the operating system. They're getting all the way down into the firmware at this point. They don't come in the front door with a marching band behind them and set off ransomware everywhere. They come in quietly, covertly, they live off the land, and they operate in your environment with your tools the same way you do during the same working hours that you do. So these kinds of firmware attacks, they bypass all those other protections that we've been talking about so far. Not the least of which is why it matters now is we're in the Baltics. You guys are adjacent to a gray zone, hot conflict, so this is particularly relevant here. And then there's a lot of other options that we've got in terms of policy. I live in the policy space on a regular basis. It takes a long time. Regulation is never fast enough. Technology and hackers move way faster than laws do. So we've got to find some options to do basically multiple things at the same time. And then there may be situations where control over your environment is actually more critical than the uptime. So you need to gain control of your environment because it's already down, for example, and how do you get it back up? So in case you didn't think that there were firmware exploits or things in the firmware space in terms of exploits, here's a list of them that already exist. They're already out there. They will take over UEFI, they'll take over bootloaders. They're persistent. You can reboot the machines and you can try to get rid of them and they're still there. They're extremely difficult to get out because they're so deeply embedded in the environment. Now adversaries, they're trying to focus in this space because it lasts. It is persistent. It will be there even when you reboot the system. We just talked about Volt Typhoon in the previous presentation. They're very, very good at this as well. They're actively targeting these things. GRU and Sandworm, they've already done this as well, also executed with lots of patience. And PLA-PRC doctrine has been openly documented around gaining persistence during peacetime so that they can actually have wartime preparation when needed. So this is happening. It's not like it's a mystery or a myth. So now we're going to talk about the trust layers when you have any kind of a system, especially in the OT space, because when you're operating in operational technology or industrial control systems, there are devices that literally just have hardware and a firmware and a configuration file. Like, that's it. That's all it has. There are also OT things that feel and look and act a lot like IT, like your HMIs and your servers, for example. They go all the way up into an OS layer. So we start with the hardware, which establishes trust, and we'll talk about what level of trust we're at here, but it's where you start. Then you go into the bootloader, and that kind of executes what the system can do when interacting with the hardware. The UEFI initializes everything, allows to connect to multiple devices if there are other components on the board, and then the firmware manages all the logic between the operating system and the board components in order to behave. So what will the system be allowed to do based on interactivity? And then applications in the OS layer, they obviously work with the OS, and then basically that's the top of the stack is the application component. So the fact that we're having to deal with this at the firmware level is actually a good sign, and that's going to sound strange, but we've done a pretty good job at securing a lot of the other areas. So much so that they've gone all the way down into the firmware to increase the attack space. So what are some of these hardware risks? When I say trust the hardware, you can only trust it so far. That's true. But I've looked at this, I've done a lot of investigation into this. Tampering with hardware is actually very difficult because you have to mass produce the issue, or where when you make it, it is mass produced. It's difficult to make one-off hardware here and there. It's actually very expensive to do so. Not that it's impossible. I mean, it's still a reality, but it's much more challenging to do so. It has a high complexity, it definitely has a low frequency, and it is testable. So you can actually, in most cases, see the hardware change. Not all, but most. And once it's in the field, it's unchangeable. So when you do create tests to look for these kinds of things in the hardware, it's there. You will be able to see it because they can't, on the fly, change that physical hardware to hide, for example. I know a manufacturer that they have to buy chips because we all buy nothing. Anything that says it's made in a country means it was assembled in that country. That's it, because we're all buying components and chips and boards from everywhere. I know one manufacturer that literally will unspool every single component before it goes on the board and x-ray it at a very detailed level to look for these kinds of things. So again, if it was designed in the hardware, there are ways to pick it up. Now, there are also things like the intellectual property blocks that can hide hidden logic and microcode. There are some foundry-level attacks that will definitely affect chip behavior as well. The chips will behave in specific ways based on the way they're designed. FPGA bit streams, RNG backdoors that can have some crypto issues, and the counterfeit components. There's even some things like radio interfaces and that kind of thing. But again, physically discoverable in a lot of cases. So hardware risks have to be acknowledged. We got to know they're there. But again, we have to start somewhere in terms of getting at this layer. Firmware is a lot easier for us to start fixing now, and hardware is a much longer-term problem for us to work on. So the priority in the firmware is we can get to this stage because firmware attacks are scalable and affordable for the attacker. This is something that is actually fairly easy to do. If you've seen a firmware package, they're pretty small. We're not talking about going through millions of lines of code. It's actually a pretty small set of code that we're looking at. The good thing about the attack space for the attacker is that the compromise works across the entire product line. So typically, they repurpose firmware across multiple hardware components because of feasibility. It's just cheaper to write the software to match the hardware in a more extensible way for the manufacturer. So your OT product manufacturers aren't going to write a whole bunch of specifically different firmwares. They're going to modify a firmware package that go across an entire product line. The attack kits already exist for the major vendors. We have seen open and shared attack kits amongst the attackers out there, the sophisticated threat actors. They've already got tool sets that can break apart the firmware and insert what they want into the firmware and reissue you that firmware in a way most of the time you can't detect it. Again, once firmware is in, it is persistent. It's not something that will change when you reboot the system, because as the system boots, it loads that firmware every time. So if you affect that firmware, you affect the way the whole system behaves from that point on. It is, of course, pre-operating system execution. It bypasses anything in the operating system in terms of security, and there really aren't a lot of organizations that are checking firmware. If they get a firmware package, it's time to update the firmware, they update the firmware. There's not a lot of checking they can do other than maybe a hash or some other digital signature from the vendor. And most of the time, that's not being done. And then firmware is now the highest leverage and highest benefit attack surface. Again, you gain persistent access, pretty easy to get in, extremely difficult to detect, and it's going to be there until that firmware changes. So from a control problem, firmware trust, as I mentioned, it's just not verified. I work with a lot of OT folks. Your field engineers are really not checking that. In most cases, they just don't update the firmware. It just never gets updated. And then when it does get updated, it's usually because of a feature set that they need. So what we're doing at this point is we're trying to update. We talked about legacy systems in the last conversation. There's a lot of legacy environment out there. There's a lot of old stuff out there. It's getting replaced. It's getting, in some cases, the existing hardware will gain a new feature based on the firmware update to a new encryption algorithm. Let's say we're going to go from something like, believe it or not, like a CRC32 checksum, which really isn't encryption, but that's its method of getting integrity for the whatever communication protocol it's using, up to like maybe a TLS1, for example. Or it'll maybe update an SNMP driver, for example, from a really vulnerable one to a modern one. So as we're modernizing these OT systems, these new firmware packages are coming out, and in some cases we've seen them get compromised. Again, they're not really being checked. Now the vendors, they control the firmware signing keys. If they're even signing their firmware, they're the ones that control those keys. So we've even seen the vendors becoming a target for the fact that they're the ones being that sign, and in some cases they're not even signed very well. The next piece is secure boot. The way secure boot works with firmware is it enforces that vendor trust by default because the vendor keys allow the rest of the boot chain to exist and occur. So when you start to modify things, if anything changed in there from the vendor's perspective, that boot won't happen. And as I mentioned, most operators, they just don't inspect the firmware. They really have no capability to do so. Most of your field engineers and your field technicians, they wouldn't know what to do inside of a firmware package if they even got in there. Now, the compromise of a vendor, this is one of the key pieces, as I mentioned, even those firmware signing keys and other components. If you compromise the vendor, then you compromise the firmware. And this is becoming a bigger target, not just the entity receiving the firmware, the asset owner, the electric utility that's loading the firmware, it's the vendor that's getting attacked. So we're seeing a lot of the Schneiders, Rockwells, Emersons, Honeywells, these standard vendors that we all use. They're tightening their programs significantly so that they don't become a bigger target than they already are. The other piece is a lot of them use pre-existing open source. Not because, I mean, yes, it's inexpensive, but usually it works really well. And it's been around for a long time. It's been tried. But when you get things like a Log4j or other things that are firmware-based inserted open source into your firmware, or the VX one that came through that was an SSH attack, so you'll see them going further down the stream to get into the open source environments, and then that will come in and get embedded in the firmware as it goes through. So there's a lot of ways that the vendor can even become a channel themselves. And then, of course, control of the firmware equals control over the infrastructure. That's the kind of the fundamental understanding. So the limits of compliance here, being an ex-regulator, I call myself a recovering regulator. NIST 2 is good. DNA is on the way. CRA is there for Europe. You've got a lot of really good things going on. Most of this is going to give you some transparency at best. It may drive some changes in behavior, particularly CRA, but these things move slowly. And they're not extremely prescriptive. There's a lot of latitude for interpretation, shall we say. Now, both of those do improve things like vendor responsibility, vendors reporting, so you're going to get some good out of this. I don't want to say that this is not going to help. It's going to help a lot. It just helps slowly and in less direct ways. So the main thing is compliance to any of these does not mean that what you're booting on your platform has integrity or is good for your organization. And regulation definitely doesn't replace things like technical assurance of what you're getting from your vendors or what's running on your system. So firmware trust still has a lot of dependence on what you've got from what the vendor is doing and what their policies are. A quote from Anissa here as well. So what I'm proposing is that we take two tracks. With emergent needs like what we're seeing in Ukraine, for example, we have to be able to respond quickly. We have to have something to do now. And then we have to have something that we're also doing behind the scenes, which of course is going to be something regulatory-wise, or better yet, just standardization. So we already know that supply chains are being attacked. We know that even certain countries have a mandate by their government to infect supply chains and to do this by practice. So what we can't do is just rip and replace all the hardware. I mean, let's just say it's a power system or a water system or a telecommunications environment. To take the system offline to fix it means it went offline. And then to buy all that new equipment is incredibly expensive, and to get it all to work together. Just for example, to recertify a power system can take a very, very long time, because if you don't do it right, it doesn't balance well, or it can hurt people. It can actually kill people. So it's not something you can just replace all the hardware and put all brand new stuff in there. And even if you did, the brand new stuff may already contain bugs in the firmware. So it's a different situation where you can't just go buy all new stuff and fix it that way. So we also have to try to do something in the standards space, but that takes a long time. So in this two-track approach, my recommendation basically is to do some immediate remediation, recovering trust of our environment where we've got firmware problems, at the same time work on international standardization on things like, if you're making devices that go into critical infrastructure, the firmware must have some way for the operator or the owner to check and validate and make sure that it doesn't contain anything. So for now, remediation is needed quickly because we have situations where firmware is already infected, it already has backdoors, and it's already installed in environments. Critical infrastructure is already depending on a lot of what I call foreign manufactured. Again, that's anywhere. That doesn't necessarily mean it's Huawei gear. That could also be Cisco gear. This is nation, not specific. Cost prohibitive investment in hardware is one of the bigger problems. You can't just buy all new stuff. That's not only the cost of the hardware, but the cost of certifying it in those environments as safe to use. The existing supply chain already has firmware persistence problems. As I mentioned, we've just got some handful of public examples. There are others. And then the vendor update channels are trusted, but they're vulnerable to compromise. We've already seen watering hole attacks on vendor download sites for firmware where they've replaced it with rootkitted firmware. Those legacy systems that we talked about and that were talked about in the last presentation, they're going to be there for a while. They were built to run 30, 40, 50 years, and they're likely going to run 50 years or longer in a lot of cases. They are working well, there's no need to replace them, and it costs a lot. And as I mentioned, the adversary does already exist in the field. We've already seen this in a lot of cases. So I don't want to try to wait for long-term solutions. We should prepare, in the event that we need to, the ability to go ahead and actually take control over our firmware. So what are some of the things we can do with this firmware, right? You want to recover this control of the firmware without replacing the hardware. So what we've done this in some labs. You can extract and analyze what you've got already on the box. So the firmware that's loaded on the system is typically a little binary file. You can pull that down and you can examine it. There is a lot of challenge to this, but it's not that hard. It can be done to reverse and remove anything that is there in terms of persistence. So you can actually see what the attacker inserted into the firmware, because again, they're not very big packages. Then you root the device itself. If you need to, you can flash the UEFI, you can flash other parts of the BIOS and the firmware, and then you take control over the device basically with your own kit. Then you can configure a secure boot chain where the operator controls it, and then re-sign your own firmware with your own trusted keys, and then deploy that validated firmware across whatever number of devices you've got. Because typically, if you're like rolling out substations, for example, you don't buy individual stuff, you buy the same stuff for a whole bunch of substations at the same time. So it's pretty easy to do this at scale within your environment. And then you can restore local authority over the device. This means you own the firmware, you own the boot, you know everything about that, and now you control your environment again, and with a fairly high degree of assurance, you can guarantee the attacker is not in your firmware anymore. Now, some of these things, as I mentioned, this is not necessarily the easiest solution. But we're at a stage in the problem where we're looking at hard solutions to very hard problems. How do you get an attacker that's rootkitted your system? How do you get them out of a persistent environment? That's not an easy problem to solve. So I'm not proposing that this is easy, but I'm proposing that this can be done and should be done. So proprietary bootloaders, they definitely limit transparency. There are bootloaders on the system that are encrypted. They're very difficult to get into. We can still get into them. Some of them actually take things like hardware chip glitching and freezing attacks. There's a lot of craftiness that sometimes that you have to do to get them to actually give up keys. so you can get in there and rewrite everything. Secure boot, again, that's a different one because you can't see the process. It's typically a hidden process or an encrypted process. And then locked firmware that comes with keys. Those entire ecosystems, of course, the vendor doesn't want you in there because they've got proprietary stuff. Once you get in there, you can actually see what's there. Unsigned firmware, there's some of it out there. But the tools to actually get into unsigned firmware, there's not a lot of those tool sets out there. We're starting to see more and more developers actually writing firmware kits to help with this as well. So, and they're trusted kits. They're not just things you get from the black market. Most firmware analysis, again, it's not a very big file, but you do need to know what you're looking at. There's a lot of hardware addressing, a lot of hardware components. It's not your typical Java developer or Python scripter that's going to understand firmware kits. It's going to be a much different level of skill set that you need. Of course, if you have a vendor contract and the vendor says you're voiding your warranty by doing this, you have to look at the challenge there. Is it an operational situation where you need to do this to regain control of your system? And it's worth saying, we're going to go ahead and get past this vendor warranty issue because the vendor is being restrictive or challenging, but we want control of our operational environment. And then regulatory and export restrictions, you do need to worry about that. In some cases, there are laws around how you have the encryption and other mechanisms you've used in your environment. They may not be exportable to some countries in some situations. So just know that there's other legal challenges that come with this if you're trying to move the technology around. So how do you typically do this? We've done this in the lab. It's challenging, I'll tell you that much, but it's actually easier than we thought because we expected this to be far more difficult. Definitely some lab tests, and we've got some situations where we have actual like live power systems, like distribution systems. We've gotten up to all the way up into transformers, inverters, battery energy management systems, and a lot of the different things you find in power systems in general. So we lab tested first, extract the firmware image. We do a lot of static and behavioral analysis where you model what it behaves. You put it in a sample hardware environment and you just beat it to death and see how it behaves. Once you get it to a place where you can see what's there, you can repackage the firmware and sanitize it so that it's known good. And then you have your own keys, you re-sign it, and then you deploy with a rollback, which basically says in the event that things go bad, you roll back to the known good state, and then you log and monitor the integrity. This should look like a standard kind of operational process, especially for anybody who's done hardware work. So what are some of the risks and trade-offs to doing this? The devices will brick. We've definitely bricked a few devices. We haven't let the smoke out of too many of them. I think maybe one, but most of the time it's just breaking in the process. The vendors kind of design it that way as a tamper safe. So it's going to take some challenges and some trying. High assurance testing is required for safety critical systems. If you're doing this in chemical or certain manufacturing or refining operations in particular, you can actually cause the system to go boom and kill people. So you have to have a lot of different extra additional layers for safety critical systems. And the firmware keys, those have to be secured, of course, to minimize insider risk. Because once you have people doing this and re-signing that firmware, whoever is writing that new firmware and signing and deploying that firmware has to be a trusted individual, and you have to manage those packages as well. I certainly agree with Anastasia. You should do this as much in an automated and multi-stage checked way as you possibly can. And then vendor cooperation is likely going to be non-existent. Vendors don't like it when you basically mess with their firmware. Again, if the vendor is not cooperating with you and you need control over your environment, you may not have any other choice. So just understand that you're likely going to have a pretty high friction relationship with your vendor. This is where we're trying to move the standardization and regulatory space to force them to where they are going to play nice in the other direction. Again, those things take time. I've written regulation. It takes forever. And then balance the hardening with the operational continuity. You're going to have to figure out where this makes sense, where it's needed. It's not going to be needed everywhere. I wouldn't go do this just because you think it's a good idea. There's, like I say, there's operational need for this kind of a response. And then last but not least, I work in the OT space. This is where cyber meets physical. When you click on something, a pump moves, a valve opens, pressure gets released, things can be dangerous. So safety can't be compromised at all in the process, unless, of course, this is more safe than the unsafe operating conditions that you're already under. So we're trying to get to a place where we have firmware sovereignty. We have to get firmware trust from the vendors to the operators. We have to shift that ownership and the reliance, the accountability and the transparency. That's got to go from the vendor to the operator so that you know what you're getting, you can confirm what you're getting so that you know you've got a safe operating environment. The devices should boot only things that you know you've verified. And again, we're getting things that are verified from vendors that already contain rootkits and dangerous things. So the next thing is the signing keys. You should have control over the keys that you sign for your firmware. The vendors shouldn't. Vendors aren't going to like this in a lot of cases, but we have to shift to a place where you own your own things. And you should not have blind trust in their update channels, of course, because vendor update channels, again, like I said, they've been watering hold, not the least of which is we've seen what happened with SolarWinds and several others where they just go further and further up the chain to infect what's coming down the vendor pipeline. Okay, and then supply chain controls, it's not just something that they certify it when you buy it, because when you buy it, you have to maintain it. That's the problem. So anything you get as an update can contain the issue. So it's not just, well, we bought it and it was secure. It needs to be the entire life cycle of that device. And then extend below the operating system where we're talking about that space between the physical hardware and the OS. That's the new territory because that's the persistent territory. And this is how we regain control over our infrastructure. Standardization is again, the slow-moving regulatory part that I'm talking about. So if your situation is bad enough, and you know you've got firmware that's pwned by your adversary, and you want to gain operational control back, the previous recommendation set is for you. Strategically, you can continue to monitor the heck out of everything, which you should be doing already in the OT space, and then wait for things like standardization to occur and participate in the standardization effort, where we need to do things like a standardized firmware model, where it contains the same things the same way in an inspectable, transparent method. Open inspectable firmware for not just OT, but anything in the industrial space, and even IIoT, and I would even argue just IoT, because it's connected to the internet in a lot of cases. And when these companies, especially when it comes to IIoT and IoT, these companies spawn overnight, they sell 1 billion devices, and then they go away in 2 years. And then either their stuff is bricked, or it's just left out in the open forever and ever to become a problem over time. So if we had these standards, we could actually go in and own those devices again after the vendor leaves the system. So this is not just a good idea for OT firmware. Reproducible builds to prove firmware integrity. This is where you can take the same thing that they've got, build it yourself, and come up with the exact same result. So if you've got the components, you can build in your environment, and you should get the exact same match of what they built in their environment. So this gives you the kind of cross-reference capability within standardization. Independent verification of boot sequences. So as the system is booting, there are checks and gates along the process, whether it's the UEFI handoffs, the different ROM handoffs, the different memory allocation locations. All of these areas have little interesting checkpoints where we can introduce methods to verify that this boot sequence is safe, or what is expected, at least. And then secure update process with provenance, so that when you do get updates from those vendors, there is some sort of chain of custody that's coming through there, more than just a hash that's on the website where you go to download it. You need a little bit more verification than that, because the attackers are already there. They're already repackaging their own firmware and putting the hash on the site because they've owned the site. So you can't just take a hash value and say that's good. It's going to take a little bit more than that. And then, of course, the operator-controlled firmware signing, so that when you sign that firmware, the operator can validate that that's exactly what is in the environment, and they can look across their fleet for anything where the signatures don't match. Of course, and then lifecycle support beyond the end of service or end of time for the device. When the vendors go away or the vendors no longer want to support that platform, there are a lot of companies that still operate end-of-life gear. I mean, again, it's expensive, it's challenging to replace that gear, so they run it well beyond its lifespan, but this gives you the chance to maintain it beyond that lifespan versus having immediately to replace it. And then, of course, the foundation for long-term supply chain resilience. So let me give you a grid risk example. Stability now depends on firmware behavior, period, because a lot of our gear is firmware-based, and it is literally just a firmware and then a config file, like a PLC, an RTU, a FEP, an IED, a lot of the field equipment that we use. Inverters, battery systems, they're already doing this. We've seen interesting firmware logic in a lot of battery systems already. There's coordinated firmware manipulation. This can definitely disrupt grid stability. So as we're looking to use a lot of renewables, and we balance our system with these battery backups and other forms of renewables, almost all of them use these inverters, and there's millions of them out there. And in a lot of cases, they're almost all vulnerable. Then, of course, distributed resources can be used as an attack surface. What we're worried about there is the instability that can be created in grid environments by using these firmware-level attacks without having to actually go through and attack humans or OS. So we have an opportunity. There's the main thing here. There is some US action that we're trying to get started as well. You don't have to do it with the US. This is just a good idea with everybody. But I want to just get the idea out there so that everybody thinks about this. And then, first things, take action. These are all the list of things we can do. The key here is to shift the trust back to the operator. We want to know that the operator can have a controlled environment that they own. Now, closing thoughts. Can't guarantee all firmware. Can't replace all the hardware. Can't wait for perfect standards. We have to do something now. We should at least be prepared in the event that we need to do something. And then, of course, firmware control has to be something that you engineer versus just trust. Thank you.
Patrick, thank you. Just one quick follow-up question from Menti, so we don't ignore our dear audience. I like this one. What if the vendor is not hacked but was malicious from the beginning? Is there a meaningful way to verify a vendor microcode does not contain a backdoor?
Yeah, there are ways to do it. Again, they're not easy because if the vendor is malicious and they're inserting bad code into the firmware, they're likely going to hide that with things like secure bootloaders and keys. So again, as I mentioned, there are ways to do this in a lab. Definitely do it in a safe environment. Don't do this on a live system. But there are ways to do this. They're not easy. They're actually very challenging to do, to get in there, especially if the vendor is intentionally trying to hide that in their firmware.
Probably costs some money to do that as well, right?
It's actually not that expensive.
Yeah?
Yeah. It's just the skills most of the time.
Well, that takes financing as well, right? Patrick, thank you very much. And a gift of gratitude from CyberChess. So you remember us. Thank you. Thank you, Patrick.
Cheers.
Patrick Miller, a round of applause.